Hello, people. 2 people so far. Let me do the usual stuff. Where are you, stats? Yeah. Here are the usual links to the attendance. Please fill it out, as well as the link to tutoring and the end of quarter evaluation. I'll throw those up there again. There are the usual links. Attendance, tutoring, and the end of quarter eval. So far, I don't know which students from which classes have filled out my eval, but a number of them have. So if you have, thank you. If you have not, please go do so at your earliest convenience. What else did I want to mention? Reminder that you can decide to take this class pass no pass up until, I should actually get the right date here. I think it's June 5th or June 4th. Let me double check. I believe it's June 5th. You have until June 5th to decide if you want to take the class pass no pass. So if that's something that you are thinking about, just make sure to, if you're going to do it before the last date possible. You should also talk to your advisor if you are concerned that it may or may not be allowed depending on your major. So I would definitely look into that. What else? I feel like I got something else. Oh, I know. I wanted to share with you guys just something non-statistics related, just something from life. I wanted to share with you guys what I did over the weekend because I thought it was kind of fun and worth sharing. So if I can find the dumb thing, 1 second. Let me just do it this way. 1 minute. Sorry. Let me stop trying to share my screen for a second. And let me grab this. Let me bring it over here. Okay, let me share my screen. I think I can just share Paint. Yeah, it's cool. So here are some pictures from my weekend. I went rafting with some friends and we camped out overnight along the Cache Creek. I want to say Cache Creek River, but I guess it's a creek. I don't know. Along Cache Creek, which is very nice. The weather was beautiful, not too hot, but definitely warm enough to be out on the river. So here's a picture of me next to some muck. And here's a picture of me at the campsite wearing my favorite jacket. And here's a picture of me along with my friends Zach and Liam, his son actually did most of the guiding on the trip, which was pretty cool. He was very competent. Zach definitely took us through the rough parts, but Liam was doing most of the guiding for most of the trip. And then here's a picture of myself over here and Sarah, who some of you might know, who worked for the AATC as well. Sarah is Zach's wife and Zach's her husband. Liam's their kid. Here's us on the river just cruising down, having a good time. So just thought you guys might be interested to see some pictures from life because, you know, people are doing things on occasion. So yeah, that was what I did this weekend. It was a good time. It was good to get out of the house and do something. Yeah, thank you. I had fun. I was happy to be out in the world. Kind of felt almost normal, right? It felt like a normal camping trip, you know. We saw lots of other people. They were way over there. We were way over here. Got kind of thrashed up a little bit. If you can, let me show you guys. You can see my knee. I definitely there was a lot of brush. Anyway, enough of that. We had fun. So here's the attendance and stuff again. Please do go fill out the attendance as usual. What kind of questions you guys got? I'm imagining maybe you want to talk about hypothesis testing, but let me know is that true, or are there other things you are interested in talking about? Yes. Okay. Yes. Okay. So one thing I'll say first of all, would you please? Yeah, sure. We're all on board with the hypothesis testing for sure. So first thing I'll say is I definitely did do a lot of hypothesis testing stuff on class on Thursday. So if you weren't here, which is totally fine, I would recommend watching the video from that class just because I feel like I did do a lot of good examples. Is anyone here today who was in class last Thursday? I don't remember who all was here. So me. Okay. So I wanted to try not to like duplicate my examples because it feels like lame to see the same examples over and over again. I might do some of the same examples, but I'll try to do some different ones. Excuse me. That said, for all of you that have, for everyone, I would definitely recommend watching the video from whatever the date was last Thursday, the 21st, just for more examples of hypothesis testing. So let me grab, man, sorry, I got very burpy all of a sudden. Let me grab the examples I had ready to go. And we'll try and do some one tail and some two tail ones. Sorry, they're over here. So, and actually, I kind of want to also take a moment to kind of relate confidence intervals and hypothesis testing because they very much are related to each other. So I'm going to do that while we do this. So let's look at this example. So let's look at this. So let's say we have we're doing a study on body temperature. Why not? Interestingly enough, there have been studies done on body temperature, and they've found that 98.6 might not actually be the body temperature that we all have. It might be a little bit lower than that. Whatever. So let's say we have 106 temperatures taken. And we have only the first 10 temperatures to work with. Let's actually not start with that. Sorry. Let's just say we have 106 temperatures taken. Let's go with that. And we know that the mean of our 106 temperatures taken is 98.44 degrees Fahrenheit. And the standard deviation, which is a sample standard deviation, where it's a sample of 106 people, is 0.30 degrees. So before we go ahead and talk about hypothesis test, let's talk about constructing a confidence interval. So I would like to construct a 95% confidence interval for the true mean of average body temperature. So I want 95% confidence interval for mu, which is the true average body temperature. Okay, so the way we're going to do this is the usual way. We're going to say that, no, come on. Sorry, I'm a little crooked here. So the way we calculate this is we're going to say that the confidence interval is going to be given by x bar plus or minus our z-score, the z alpha over 2, times our standard deviation divided by the square root. Our sample standard deviation divided by the square root. In this case, and so depending on the source you're using, I think your teacher has talked about using 2. I feel like 1.96 is the more accurate value for a 95% confidence interval. You should definitely adhere to what your teacher says you should do. I'm going to use 1.96, or it's close enough to the same that it's not that big a deal. So in this case, it's going to be 98.44 degrees plus or minus the z-score, which is 1.96. And that is probably one for 95%. I would probably just recommend memorizing, whether it's 1.96 like I think it is, or 2 like your teacher says it is. Either way, you should definitely just commit to memory whichever value they're using. And then we've got our S, which is 0.3 divided by the square root of 106. And if we calculate this, it's definitely something I need a calculator for. So, and I think anyone will need a calculator for, really. So let's see, I've got 0.3 divided by the square root of 106, which is about 0.029. And then, right, that makes sense because 0.3, square root of 106 is about 10, so 0.3 divided by 10 would be about 0.03, so 0.0297 seems reasonable. Times 1.96, which is about 0.057, we get 98.44 plus that value, which is the higher value. So I've got 98.497. Let's round that up to 98.50. And I've got a lower value of, let's see, 98.44 minus 0.057. Will give me 98.382. So I'll throw that down to 98.38. So that is our confidence interval for the true mean of the average body temperature, meaning we are 95% confident that the true average body temperature is between 98.38 degrees and 98.50 degrees. Okay, let's compare this to a hypothesis test so I want to test the hypothesis that the true average body temperature is 98.6 degrees. So hypothesis, which is, trying to, by the way, I don't know if I showed you guys, I think I did, but I got a big old stack of pens, which I'm very happy to have. I think I was very happy last Thursday about my big stack of pens, but just in case I wasn't showing you, I'm very happy with my big stack of pens. So for hypothesis, we want to test the null hypothesis that the true average body temperature is 98.6 degrees. And now I actually have to think about this for a second. What is the alternative? Is the alternative, like, are we, so if we pretend, and I think it's kind of important in this case to think about like what we know versus what we're supposed to know. So if I'm trying to test the null hypothesis, the average body temperature is 98.6 degrees, I really don't want it to be different, right? I don't want it to be above or below. I'm not saying it's okay for it to be like 98.6 or higher. That doesn't really make sense. So in this case, our alternative really is that sorry, there's a mu not there, is that the average is not 98.6 degrees, right? That it's either above or below some way far enough. So we're trying to test this hypothesis here. So this is definitely going to be a two-tailed test, right? Because if it's too far above or too far below, that's going to be evidence that we should reject the null hypothesis in favor of the alternative. What I'm trying to say here is you couldn't just start off by saying that I want to test that the alternative alternative is that we're below, because we already have this data that's showing it's below. Unless, of course, we specifically thought already, like if we were thinking, we think the average temperature is actually below 98.6, then it would make sense. But if we just think it's different, so really kind of, I'm saying a lot of words here. It depends on the context of what you think is happening, right? We are just trying to test if it's different. All right, so let's see. I want to test this alternative hypothesis. And so there's two ways to think about doing this. We are thinking about our confidence level being 95%, which means our alpha is 0.05. Right, we're doing a hypothesis test with alpha below 0.05, which definitely needs to be specified before we actually start doing the work. Sometimes people like do the test and then they're like, oh, I got this value. I'm going to go back and say my alpha was this, so it gives me what I want. And there's a no-no, we're supposed to decide alpha first. 0.05 or 5% is the typical level of that. So here's what we're trying to say. We're trying to say if the mean was actually 98.6 degrees, what is the likelihood of seeing the data that we got? And if it's less than 5%, we're going to say, well, then we probably don't actually think the mean is 98.6 degrees, right? If there's a small chance of seeing the data that we actually saw with the assumption of this being true, we're going to say, well, our assumption is probably false then. All right, so again, there's kind of two ways to do this. one way to do it is to compare our test statistic with the actual z-score. The other way is to compare our actual p-value with the alpha. Let me draw a picture, which I'm sure you've seen this picture already. Still good to see. So here is our mu naught equal to 98.6. And I know that since our test average or our sample mean is above that value, right, so below that value, 98.44, I'm going to draw it like that's the case. So here is our value of 98.44. And we're going to find our z-score that goes with this, or our test statistic. And here's the idea. And I think this one ends up being rejected. I'm not actually sure, but I'm going to draw it like it is. So let's pretend so here is our z-score of 1.96, or here is our z-score of negative 1.96. If the z-score for our data, which I haven't actually calculated, let's calculate the z-score. Sorry, I'm just getting ahead of myself here. So then we calculate the z-score, or the test statistic, right, is our mean minus the null hypothesis mean divided by the standard deviation, which is our sample standard deviation divided by the square root of n. In this case, that's going to be our 98.44 minus 98.6 divided by s, which is 0.3 over the square root of 106. Calculator time. Let's see. Sorry, I think I'm simply breaking my stuff. Okay. Let's see. So 98.44 minus 98.6 is negative 0.16 divided by, or really you could flip the multiply and say it's times the square root of 106 divided by 0.03. Sorry, 0.3, not 0.03. Whew, that's big. I'm getting negative 5.49. So this has a z-score of negative 5.49. If I can make here, sorry. So here's what we're saying. We're saying that if we actually saw this data, at least here's what we're saying with this particular piece of information, that this average temperature, 98.44 degrees, is more than 5 standard deviations away from the mean. It is really unlikely to see an average that's 5 standard deviations away from the mean if this is actually our average. So here's one way we can reject the null hypothesis. We can say that since our z-score, since negative 5.49 is more negative than our 95% or our alpha equals 0.05 level, right, which is negative 1.96. Oops. Our test statistic is further away from the middle. It means we reject the null hypothesis that the mean is 98.6. In favor of the alternative, which is that the mean is different. We're not actually specifically saying it's less. We're just saying that it's different. We have evidence to show that it's not 98.6 degrees. Another way to do this. Now this one's going to be kind of dumb because it's not going to be on the table. But another way to do this would be to say, okay, I'm going to take my z-score of negative 5.49 and look up the value on the z table. Now, if you look at the z table, that value isn't on there, right? Let me just share my screen with you guys for a second. So, one sec. Yeah, trying to share a screen here. So if you look at our z table here, our z table only goes, this one even goes further than most, it goes to negative 3.99. we can say that the area under the curve is definitely less than 0.00003. So for our actual score here, right, that area is less than 0.00003. Whereas, and so I want to be really clear, this is why the two-tail part is important. The area that's to the left here, right, that area isn't 0.05, it's half of 0.05 because it's a two-tail test. So this area is 0.025. And so here's what we're saying with this 0.00003. We're saying that there is a 0.00003 chance, actually that there's less than a 0.00003 chance of seeing this kind of data if it were true that the mean was actually 98.6 degrees. Or you could say, right, if you move the decimal over 2, there's less than a 0.003% chance of seeing this data if the mean was true, which means we should probably reject the null, not probably, we should reject the null hypothesis, right? Because there's a super small chance of actually seeing this data if this null hypothesis is accurate. So that's kind of the whole idea. And I know that for Nandari's students, he at least in the things I've read from his class, he's definitely doing it more this way, where you say if your z-score is further away from the middle than the z-score for the confidence level you're at, then you reject. But it's equivalent to say if the area to the left, or if it's over here to the right, is less than the area of that's associated with the particular z-score for that confidence level, then you also reject, because what you're saying is there's that much percent chance or the probability of seeing that data, which is less than the level we're testing at. Sorry, I just should stop sharing before I start pointing at the board again. So that's the whole idea with hypothesis testing. You're just trying to say, if the chance of seeing this data is really, really low, how low? Alpha is usually the level, whatever alpha is, it's often 0.05. Then we're going to reject the null hypothesis in favor of the alternative hypothesis. Let's look at more examples. Sure. Just 1 second here. Do that one. That's later. Oh, here's awesome. I just found more. So I was grabbing problems from a different place, which are more like confidence interval questions, which obviously come up with maybe some weird z-scores on occasion. But now I just found a whole slew of other questions I can ask. Awesome. So look at this one. So we want to test the hypothesis. We want to test the hypothesis that smokers get less sleep than the general public, which gets an average of 7.7 hours of sleep. So that's kind of our null hypothesis, right? The null hypothesis is that people get 7.7 hours of sleep. Okay. We sample 50 smokers and find that they on average sleep 7.5 hours. Also, let me just, let me give you guys the attendance one more time, just in case anybody missed it. Attendance and the tutoring link, and of course, the link to the end of quarter evaluation, which I would appreciate everyone doing if you haven't already. So we find that in our sample, the average number of hours of sleep is 7.5 hours, and the sample standard deviation is, I think, half an hour. Let me double check that number. Yeah, 0.5. Okay. Does the data suggest that the smokers get less sleep than the average of the general public at the alpha equals 0.01 level? So does the data suggest that smokers get less than the average of the general public. Okay, so we're going to do, I'm going to do it both ways here. But first we have to write out what our null and our alternative hypothesis. So the null hypothesis is if they do get the right amount, the average amount. So the null hypothesis we could write as the average amount of sleep they get is 7.7 hours. The alternative hypothesis, okay, so let me ask you guys, is the alternative hypothesis that the mean is not equal to 7.7, that the mean is less than 7.7, or that the mean is greater than 7.7? One of these for sure doesn't make sense. Which one can we rule out right away? That it's not equal, that it's less than, or that it's bigger than? Any guesses? You guys? Yeah, exactly. We can rule out that it's greater than because we know we're trying to test, right? We think that the mean is probably less. So then the second thing is, since we think that the mean is less, right, that smokers get less sleep on average, then it's not a two-tailed test, right? We're not trying to see if the mean is greater than or less than. We are coming into this with a thought that, oh, they probably get less sleep. So we're testing for that specifically. So we're not doing this either. We're specifically testing the alternative hypothesis that the mean is less than 7.7, which means it's a one-tailed test. So for the first one we did, it was a two-tailed test. Half of the area was over here, half of the area was over here. So, right, there was 0.025 there, there's 0.25 there. And that goes with the z-score being 1.96 and negative 1.96. For this case, and actually let me do it for a 95% level first, just to kind of show you guys. Right, if I was looking for, so I'm looking for a 95% level, and actually I'm going to be below again. All right, so if I was looking for alpha equal to 0.05, I would want this z-score to have 0.05 area to left. So if I look back at my z-table, let me share my z-table for it with you guys. Back at my z-table, I'm looking for the area in the middle to be 0.05, which is looking like it might be somewhere in this row, maybe down below. Looks like it's right between these two. So I would say that my z-score for, if it was a 5%, that z-score would be a negative 1.645, right? It wouldn't be the negative 1.96, right? Because it's not a two-tailed test, it's a one-tailed test. But since it's a 0.01 level, let's find that instead. I think it's going dark. Now let me see if I can get a little more light. It's a little bit better. All right, I should stop sharing my screen so you guys can actually see what I'm doing better. So in this case, I want same kind of idea. Here's my null hypothesis or my null average where the mean is 7.7. And down here, I want this to have alpha being 0.01. So now I'm looking at my z-table for that. And again, I don't remember which z-table you guys get to use, but I like the one I have here, which I think I've sent you guys before. If you're looking for 0.01, that's going to be way higher. It's going to be like somewhere between here and here. It looks like it's between those two values. So I'm guessing it's a negative 2.35 for 0.01. It might be slightly different than that. So if my one-tailed test was greater, right? If I thought my alternative hypothesis was that mu was greater than 7.7, then my z-score would be positive 2.35. All right, so let's do it both ways. We're going to calculate our test statistic, and we'll see how to do that. So you can reject either by saying your test statistic is further away from the middle than your z-score or your t-score if it's t-score 1. So if our test statistic is further away from the middle than negative 2.35. Or you can say by finding the p-value, the area associated with your test statistic, to be less than 0.01. All right, they're both the same thing. So to find a test statistic, it's going to be r score minus the mean, sorry, the null, the hypothesis mean, divided by our sample standard deviation, divided by the square root of n. Okay, that's going to be 7.5 minus 7.7 all over 0.5 over the square root of 50. So hopefully these numbers aren't totally whacked out. That's going to be negative 0.2 divided by 0.5 over that. I probably could have just gotten to the calculator. Let's see what we get. So I get negative 0.2 times, or sorry, divided by 0.5 over the square root of 50. To be honest, what I'm actually doing is I'm doing negative 0.2 times the square root of 50 and then dividing that by 0.5. And I get 2.8, I get negative, sorry, negative 2.83. So here's what I can say. This test statistic is further away from the middle than my z-score at the alpha equals 0.01 level. So I can reject because my test statistic is right further away. I'm more than 2.35 standard deviations away from the mean, or from the null mean with this data. Or you can take that number, look it up in your z-table. And so if I look up that number in my z-table, let's see, so I go to negative 2.83, which is right here. The p-value, that area is 0.0023. So sorry, 233, I think. The p-value is 0.00233, which is definitely less than my alpha value, which is 0.01. So if your p-value is less than alpha, right, this means there's only a 0.00233 chance or a 0.233% chance of seeing this data if it were true that the null hypothesis that the mean was actually 7.7 hours. So here's what we can say. Our data is sufficiently strong enough to reject the null hypothesis in favor of the alternative. So we're going to reject the null hypothesis that smokers get 7.7 hours of sleep in favor of the alternative, which is that they get less than 7.7 hours. We don't actually know how much less. We're just saying that it is very unlikely that they actually get an average of 7.7. It is much more likely that they get an average that's less than 7.7. Okay. Let's look at this next one. Let me ask you this actually. Have you done ones with t-tests? Or has it all been z so far? Let's see here. So let's do this one. I'm going to do one of the ones we did last time because I think it's a good example. So this is going to be an example of a t-test one, which is slightly different. And I did do this one last Thursday, but I think it's a good example, so I think it's worth looking at. So a tire manufacturer is considering using a new type of material for their tires. They need this material to stop the car at an average of 125 feet after the brakes are applied. If there's evidence that it takes more than an average of 125 feet to stop, they won't use the new material. Less would be perfectly fine, right? A shorter stopping distance is perfectly fine. Longer stopping distance is perfectly dangerous. So we're going to go with a null hypothesis that the average stopping distance is 125 feet. And we'll go with an alternative hypothesis. Sorry, I always forget to write the H part. Right, the null hypothesis is that the mean is 125, and the alternative is that the mean is greater than 125 feet. Because then, if that's the case, if we have enough evidence to conclude that, then we're going to reject the null hypothesis in favor of the alternative, and we're going to say, well, we found enough evidence to say that the average stopping distance is greater than 125 feet. We're not going to use this new material because it's not safe enough for our standards. There's something else I want to say here. Oh, I just want to point out, sometimes people will state the null hypothesis like this, but if it's a one-tailed test, it's also okay to state the null hypothesis like mu naught is less than or equal to 125 feet. If the alternative is greater, it's okay to say the null is less than or equal. If the alternative is not equal, then the null has to be equal. So we collected data for 9 stops on a test track, which doesn't sound like very many, but maybe it's expensive or maybe it's dangerous or who knows. Dangerous, probably not, but whatever. And we got a mean stopping time of x bar equal to 128.89 feet with a sample standard deviation of 3.55 feet. Should we reject the null hypothesis? Is there enough evidence to say that the average is larger than 125 feet? Probably. A lot of these examples, a lot of these examples you end up rejecting because that's what we want to see a lot. But maybe we'll look at different numbers here to see if we can find one that we don't reject. So we're going to calculate it both ways. Now here we are going to use a t-score, which is a little bit different as far as acceptance goes. And the reason we're going to use a t-score is because our n, right, these 9 tests, our n is not large enough to use a t-score. N has to be greater than or equal to 30. When you're talking about just averages like this, if it's a proportion, this is a slightly different thing where n times p has to be greater than or equal to 10, and then times 1 minus p. But here, we're just going to use a t-score because n is less than or equal to 30. And we have an unknown actual standard deviation, right? We only know the sample standard deviation. So we're going to calculate our test statistic. Equal to our average, our sample average minus our null hypothesis divided by s over the square root of n. And that's going to be our score that we're going to compare with a t-score. That's right. This isn't our t-score, this is our t-score. Before, we were calculating a z-score, which I know I didn't write, that's a z. Here we're calculating a t-score. And the reason we get into t is because our n is small. This is going to be x bar, which is, where'd you go? 128.89 feet minus 125 over 3.55 squared. And the numbers are already written out for me, so I'm just going to tell you that value is equal to 3.29. And you know what? I often forget to say what the alpha level is. Alpha is going to be 0.05 here. And now it's a one-sided test, so we're not going to, oh, well, in fact, so if it was a z-score and it was one-sided, we wouldn't be using 1.96 for our score. We'd be using 1.645 because that's the one-sided z-score that goes along with alpha being 0.05. Right, which is again, right, if we're looking for alpha equal to 0.05, right, that's the area here. If it was a z-score and one-sided, it would be 1.645. It's whenever it's not, it's a t-score. So here's where things get a little bit weird. Do I have the t-table up? I do not. Actually, let's not do that just yet. Sorry. No, we need the t-table. Apologies. We need to go look. So the thing is, we need the t-table. And the t-table is a little bit different than the z-table, as I know you guys know. So let me find the table before I start trying to show stuff to you guys. I do know where this is. Sorry, 1 second. I know exactly where it is. It's just getting there. Here we go. So here's the t-table. So first of all, we are trying to compare our score with the actual t-score. We don't actually, brain. So here's what we're going to do. First of all, our degrees of freedom is n-1, which is 9-1, which is 8. So we're looking in the row where the degrees of freedom is 8. And we see that our score of 3.29 is between the scores of 2.896 and 3.355. So that means that our t-score is bigger than the t-score that goes along with the area being 0.01. So here's what we can say. I need to draw another picture. So our t-score, which is 3.29, is bigger than the t-score. And I said that was 2.896. Right, and this score, 2.896, has how much area? Well, it has, if I look back at the table, the area associated with that is 0.01. So that area there is 0.01, which means the amount of area associated is definitely less than that. So again, there's two ways we can say we're going to reject here, and it is a rejection. We can say we're going to reject because our t-score is definitely bigger than the t-score that goes with 0.05, right? We didn't even look at that one on the table. But if you look at that one on the table, sorry, I'm going to share again. The t-score that goes with 0.05 is 1.86. Right, so that's like even further to the left. So we can either reject by saying our t-score is further away from the middle than the t-score associated with the rejection, with the confidence level, or we can say, and this is where things are a little bit more challenging to say. You can say that the area, the p-value, we don't know what it is exactly, but if we look back, sorry, I keep going back and forth between sharing the screen and not. But if we look back here, we can say, well, we know that our t-score is between these two t-scores, which means our area is between these two areas, 0.01 and 0.05. And actually, there's a picture over here on this handout that I'm looking at, right? Our test statistic was 3.29 right here. It's between these two t-scores, and this area is 0.005, right? That's the value associated with it, 0.005. And this t-score has an area of 0.01. So our p-value, the area under the curve to the right, is definitely between 0.05 and 0.01, which is definitely less than 0.05. And again, what that means is that there is a between 0.01 and 0.05 probability of seeing this data if it were true that the average was actually 125. That's a really small chance of seeing that data if the actual average was 125. So we're going to say, well, that's probably not true. We're going to reject the null hypothesis that the average is 125 in favor of the alternative hypothesis that the average is actually greater than 125, which means we're not going to use the new material because there is sufficient evidence to show that the stopping distance or the breaking distance is too large. So this is pretty much how this alternative, so I should say none of our examples we didn't reject, but all of our examples we ended up rejecting. Let's pretend for a minute that our t-score ended up being, let's say our t-score was 1.5, which is definitely, if I look back at my table, actually, maybe it's not definitely, that t-score is between 0.100 and 0.050. So if that was my t-score, I'd say, well, now there isn't enough evidence, right? We don't we don't have a less than 0.05 probability of seeing that data, right? It's a between 0.05 and 0.10 or 5% and 10%. So if that were the case, that our t-score was 1.5, we would say we do not have enough evidence to reject the null hypothesis, or we fail to reject the null hypothesis. We don't say we accept the null hypothesis. We always say we fail to reject, or we don't have enough evidence to reject. But this is kind of always the process. You find your test statistic, and then you can either say my test stat is bigger than the z-score, the t-score that goes with the level that we're testing at. And if it's bigger, then we reject. If it's smaller, we fail to reject. I should say, if it's further away from the middle, we reject. If it's closer to the middle, we fail to reject, right? Because if it's bigger, it'll be bigger on the right, or it could be more negative, which means it's actually smaller, but further away from the middle. And then, or we can say, I'm going to find the p-value, which is the area that goes with the score we have. And if the p-value is less than alpha, then we reject. The p-value is bigger than alpha, we fail to reject. But basically, with the p-value, you're saying the p-value is the probability of seeing that data if it's true that the mean is what we're assuming it is with the null hypothesis. So if the probability is small, we say, well, there's a really small chance of seeing this data. So we're going to reject their assumption that the mean is what it is, because it's such a small likelihood of getting this data with that assumption. But what I'm trying to say at the end here is that it's always going to kind of go this way. You're always going to find your t-score or your z-score depending on what kind of information you're given. And then once you've got that, you're just comparing, either you're comparing your test statistic with the z or t-score, or you're comparing your p-value with the alpha. And it always kind of goes like this. We will I think next up we will talk about comparing means from two different populations, and there's kind of a slightly different way of doing that. I think it's the standard deviation that's a little bit different, but essentially this process is pretty much always the same. There is also one for proportions, which we can talk about next time, which I'll probably also talk about on Thursday. So that's all I have for today. Do make sure to fill out the attendance. You're also very welcome, of course. Do the end of quarter eval too, and I think that's all I got. I'll see you guys either on Thursday if you want to come, or Tuesday if you do not. Take care. Hope you guys are doing all right. Just got another week after this and then finals. So hang in there. We are almost done. Bye.